Okay, everyone. In this lesson here, we are going to get an introduction to systems. Now, we have already talked about free body diagrams in this class, and we know what free body diagrams are. Free body diagrams are diagrams that shows you all the forces acting on an object. What we're going to do in this lesson here, we're going to take those concepts and we are going to expand them to systems. Now, in physics, a system can be defined as a single object, it can be two objects, or it can be multiple objects. And the way that we represent that in this class is that we always represent that using a dotted red line. So, for example, consider this illustration here. I have a physics textbook which sits on a table which is sitting on the floor. Now, suppose I ask you to represent a system using only the physics textbook. So the way that I would do that, I will circle my physics textbook with a dotted red line. And when you see that, you know that in this particular example here, this is my system. Now, suppose I wanted to define my system to be both the physics textbook and the table. Well, in that case, my system consists of two objects, and so in order to represent that, I would use a dotted red line around both those objects. So this here, in this example here, would be my system, which is made up of two objects. Suppose I ask you to draw a system that includes the physics textbook, the table, and the floor. Then you would do this. You would draw a dotted red line around everything in the illustration. It would include the book, the table, and the floor. And so these three objects would be my system. Before we get into more details with systems, I want to remind you all of an important law in physics, and that is Newton's third law, which says that for every action, there's an equal and opposite reaction. And we see this example here with two astronauts in space. So in this example here, we see that whenever one astronaut pushes off on the other astronaut, then the astronaut pushes back on him. So this is Newton's third law, which basically says that all forces in nature comes in pairs, that for every action, there's an equal and opposite reaction. If you push off on an object, that object pushes back on you. Okay, let's move on to another situation. In this particular example here, I want to show you all how the direction of forces can change depending on how you define your system. So in this case right here, we're going to focus on the frictional forces specifically. So remember, guys, that anytime you have two objects sliding across each other, there's going to be a frictional force involved. In this particular example, we have a wooden block sliding across a wooden table. So suppose I wanted to treat the wooden block as my system, and I wanted to know what direction is the frictional force acting on that system. So if I was to solely focus on this block here, I will use a dotted red line like this to represent my system. So in this particular example right here, I know that the frictional force acting on the block is pointed in that direction. But what if I change my system? Now, instead of my block being the system, what if I call the wooden table my system? In what direction does the frictional force act now on this specific object? Well, guys, we already know that the force acting on the block points toward the left. But remember, guys, according to Newton's third law, for every action, there's an equal and opposite reaction. If the table imputes a force towards the left on the block, then by Newton's third law, the block must impute a force on the table toward the right. So that's Newton's third law. For every action, there's an equal and opposite reaction. So when we change the system, notice how the force, the frictional force, is now pointed in another direction. And also, I apologize if my drawing is not perfect, but pretend that the length of this arrow on the screen is just as long as the length of the previous arrow I just drew. Okay, so I'm going to end this lesson with one more situation. I want to analyze a situation in which I have a big box sitting on top of a smaller box, which is sitting on the floor. And for this situation here, I'm going to draw two free body diagrams. I'm going to draw a free body diagram when my top box is the system, and I'm going to draw a free body diagram when my bottom box is the system. When my top box is the system, I'm going to draw a dotted red line around the box to illustrate that. So, how many forces do I have acting on the top box? Well, it should be obvious to you all that we have two forces acting on the top box. There is a force of gravity pulling downward because the Earth itself is pulling on the top box and the Earth is pulling it toward its center. There's also a normal force acting on the top box because this bottom box here is in contact with the top box. So the surface of the bottom box pushes upward on the top box. So I'm going to draw a normal force there to illustrate that. And it should be obvious to you all that these forces have to be equal because we have a system here that's at rest. It's not moving, so both the forces acting on it have to be balanced. Lastly, let us consider a situation in which my bottom box is the system. So I'm going to draw a dotted red line around the bottom box to show that. So how many forces are acting on the bottom box if we were to draw a free body diagram for this particular system? Well, if you guys notice here, we actually have three forces acting on the bottom box. Clearly, we have the force of gravity. The force of gravity is pulling down on the bottom box. That's obvious because the Earth itself pulls on every object. And hopefully you guys can see that we're going to actually have two normal forces acting on this free body diagram. And we're going to have two normal forces because we have two surfaces of contact. We have a surface of contact here between the bottom box and the top box. And we have a surface of contact between the bottom box and the floor. So there's a normal force from the top box pushing down on the bottom box. And then there's also a normal force from the floor pushing up on the bottom box. And I'm going to call this normal force from floor. And I'm going to label this normal force from the top box. Because it's pushing down on the bottom box. So now that we have finished drawing our two free body diagrams, I want to look at these two illustrations when they're directly next to each other so that we can analyze a few things. The first thing that I want you guys to notice is that I drew the normal force here and the normal force here the same color. And the reason why I did that is because I wanted to show you guys that these are action-reaction pairs, meaning both these forces are a result of Newton's third law. Remember, if the bottom box pushes upward on the top box, then Newton's third law says that for every action there's an equal and opposite reaction. That means the top box should be pushing downward on the bottom box, and those two forces have to be equal in magnitude. Another thing I want you guys to notice, that I drew this arrow here a different color from this arrow, the two forces that are the force of gravity. The reason why I did that is because these two forces are two different magnitudes. The force of gravity that's pulling downward on the top box is larger because we have a bigger mass here, and the force of gravity that's pulling downward on the bottom box is smaller because we are dealing with a smaller mass. Okay? And the last thing I want you guys to notice, on this free body diagram here, I did my best to draw this yellow arrow here the same length as these two arrows combined. And the reason why I did that is because, remember, our system is at rest. So since our system is at rest, these forces should be balanced. The system should be in equilibrium. So the two forces that are pointed downward must balance out the one force that's pointed upward. So this force plus this force should be equal to the magnitude of that force. Okay, so that's all we're going to talk about with this lesson on systems. Hopefully you guys learned a lot, and I will see you guys next time.